Good morning, guys. It is Thursday, March 19th, and it is our first day back at lecture, except it's all online now. So I hope you guys are doing great. And today we are going to continue where we left off last Thursday. So last Thursday, we started our brand new packet all on heat energy. So we've already covered quite a few pages in here. And I believe I have this posted, sorry, I got a little wet, on Canvas under files. You can access what we did last Thursday. And we are going to, again, gosh, we did so much. So hopefully you are all here. We had a fun little calculation that we did. I'm going to keep flipping. And we're going to pick up where we left off. Okay, so working a lot of word problems in this chapter with heat energy. And it's really important to remember that when heat is released, that heat goes somewhere and something else is gaining it. So we really talked about that concept. A negative Q for heat being released is equal to a positive Q, where heat is being absorbed. The negative is not a bad thing. The negative is telling you the direction of the heat flow. Okay, so negative is released, positive, it is being absorbed. Okay, so reading this problem, it says 53.5 grams of water at 98 degrees Celsius is put into an insulating calorimeter containing 110 grams of water at 25 degrees Celsius. What is the final temperature of the water once thermal equilibrium has been reached? So a little bit similar to the previous problem on the page before this that we did last week about putting hot metal into water. And we said, what would happen if you put hot water into cool water? And you guys were like, oh, the metal would cool down and the water would warm up. And that was exactly right. But we were solving for something different in that problem. This time we're putting hot water into cool water. And that's basically what we're doing. We're putting hot water into cool water and thinking about what's going to happen. Well, the hot water is going to cool down just like our hot metal did, and the cool water is going to warm up. So once again, we want two different columns of information. Okay, so we've got the hot water column and we have the cool water column. Okay, so we have the mass of the hot water. We know the specific heat of water that we used in a previous problem. Again, that's not memorized. That would always be provided for you. And all those units we went over. So again, little c, we have the initial temperature of that hot water. Now, the final temperature we don't have because that's what they want us to know. Okay. Now, for the cool water, they said we had 110 grams. Okay. It's still water. It's still the same substance, so it would have the same specific heat here for the liquid water. And the initial temperature of the cool water was 25 degrees Celsius. And we want to know the final temperature. Remember, they should both have the same final temperature because heat flows from something that is higher heat, right, to something that is lower heat until they're at the exact same temperature. So that again is thermal equilibrium. So that's what we're solving for. And it's really important that we know this expression up here. So notice we don't have Q on either side either, right? But that's okay. We don't need that because we have this expression right here. So that's what we're going to start working on over here. A negative Q is equal to a positive Q. And remember, we really need to keep track of these signs. So any negatives, I'm going to circle. Because if you make them too tiny, you might lose track of them in your math. Now, we know what Q is equal, we can see all our variables here in our equation that we deduced earlier in this packet. Q is equal to MC delta T, or MCAT as we called it. But we don't want to forget this negative. We've got negative MC delta T, which was final minus initial, is equal to a positive MC delta T. Now, we just have to be a little bit careful about getting our correct variables put into the right spot. So again, the negative Q, who is releasing that? This is the hot water side of our equation. And who's absorbing it? That's the cool water side of our equation. So we want to be careful about putting our variables in. Now, there's a couple of different ways to do this problem. The masses are different, which makes sense. The initial temperatures are different. The only thing that is the same would be the C. Now, they both have the same specific heat capacity because they're both liquid water. So if you want to make your algebra easier, you can simply cancel out the C's from both sides. And a person that does that will get the exact same answer as the person that keeps the C's in here. Now remember, we're solving for TF, so our goal is to get our TF on one side of the equation. Okay, so I'm going to go ahead and cross out my C's. Now I'm just going to stick with putting numbers in and not units in that case, because if I cancel out my C, then my units aren't going to make a whole lot of sense. But we're just going to focus on the algebra. And we have our organized information over here to the left, so we can easily put it in right here. Alrighty, so we've got our hot water side. I'm not going to forget my negative. Now, what was the mass of that hot water? It was 53.5 grams. So I'm going to have 53.5 here. I'm going to leave off my grams since I canceled out the C's. And then I've got my TF. We don't have, we're solving for that. And then the initial temperature of that hot water was 98 degrees Celsius. Okay, now that should be equal to a positive number here. So I got to leave that positive. And then the mass of the cool water was 110. And then again, we don't know the TF, that's what we're solving for, and it had an initial temperature of 25 degrees Celsius. So let me write that in there. Okay, so this is our expression that we have now. So now, basically, we've got some fun algebra to do. So thinking back to your basic algebra skills, okay, we need to distribute. And we don't want to forget that we have this negative here. So we have a negative 53.5 times TF, and then a negative 53.5 times a negative 98. We've got to distribute. And then we need to do the same thing on the other side as well. So when we do that, now we have a negative 53.5 TF. A negative and a negative is a positive. So give me a second, just like in class, I've got my calculator here. So 53.5 times 98 is 5,243. Of course, notice that is a positive value because a negative and a negative in mathematics is equivalent to a positive value. Equals, we've got 110 TF, and then 110 times 25 is 2,750. And there's still going to be that negative here because this is a positive number times a negative number. So we've got negative 2,750. Okay. Now again, there's always a couple of different ways to do your algebra. Our goal, again, is to get the TFs on one side. Okay. So I'm going to go ahead now and subtract this 110 TF and put it over here. I like to put my variables on the left, but you could have done it the opposite way and we'll all arrive at the same answer. Okay, so that cancels out. Now I'm also going to do in the same line, since we're running out of a little bit of paper here, since I have my TFs on the left, I need to move this number over to the right. This is positive, so I'm going to subtract it from both sides. Okay, so now that cancels out. Now we're going to write our new expression that we have now. Okay, so these are two negative numbers. So now we have negative 163.5 TF, okay, is equal to, now we can add these two big negative numbers together. Okay, so